Good evening to everyone. Welcome to the session of evaluation of M2M communication. So there was a communication yesterday by the government to refrain from public seminars so that we have limited audience today. Otherwise we would have had a huge crowd. So anyhow, welcome to the session. Thanks for coming for the session. And without taking much of your time, let me introduce the lecturer. He's an engineering professional graduated from University of Colorado, Sri Lanka, specializing in computer science and electronic design. He has played a diverse role from software engineer to development manager at Vertusa, and then in South Asian operation of Navantis as the CEO. India is now heading the iTerrasoft Private Limited as the co-founder and the CEO. iTerrasoft is a technology innovation agency focused on fintech, IoT and embedded electronics, machine learning and software product engineering in Australia, Sri Lanka and UK. So he has traveled down from Australia. So thank you so much again. So it's over to you.
Thank you, Mustali. Thank you for attending, everyone. And then today's session is about a topic which is really close to my heart, which is about M2M communication, which is a precursor to the well-known subject that we all are fascinated about, IoT. But in this topic, mainly I'll be spending some time to discuss what is M2M communication, and this is not a new subject, and how it started a long time back, and a brief history. And then after that, what's the relationship between IoT and M2M, and also how it fits into the bigger picture. And then also certain recent developments and new trends, and also new innovations in the same subject area. And then finally, if you have any questions, anything I can answer, we'll spend some time. That's a brief agenda. Thanks ISL, both the Sri Lankan entity as well as the New South Wales chapter in Australia, for arranging this and providing me the opportunity of really sharing some knowledge. So let's get into a very brief introduction about what is M2M communication, and eventually how it fits into IoT. And let me start with a very simple example. The smallest thing, or a very simple scenario where we have a switch and which gets connected into a lamp over there. Okay, that's a very elementary scenario. Obviously we can go there and push the switch, turn it on and off, and then accordingly we can expect the lamp to work. So this particular scenario is a human to machine communication over the wire, over some mechanism. But let's say that these lamps are connected into some sort of a sensor which sends some physical parameter like the movement or light or time or something, and then instruct a lamp or some other device to take an automated action. And in that case, that particular communication is known as a machine-to-machine communication. So not a new thing. So in this case, we have a, for an example, a motion sensor which detect the motion of people, and then instruct probably a light or a lamp connected in the ceiling to light up when there's a movement is apparent in the near vicinity. So let's get that a little bit more complicated. So in this case, there are more sensors. So in one side in the corridor we might have one sensor, and in the other side we have another motion sensor. So with that, we can make sure that from any side in this hallway or in the corridor, when people move, we can get the entire area lit up. And also maybe we can do that a little bit more intelligently. When people move from the other side, I can turn on lights in that side, and when people move to this side, maybe we can turn off the lights in that side and turn on the lights in the other side. So we will probably add some kind of a saving electricity or whatsoever. And to make it a little bit more complicated, of course, this turning on the lights during the daytime is not essential, because during the daytime probably we might have the sunlight. So in that case, even though we detect motion with these sensors, we don't necessarily need to do it during the daytime. So what we do is we pick another some kind of another device which can detect, okay, whether what is the time or whether we have sunlight or not during the daytime, and provide one more input. And depending on that input, obviously the lights can figure out, okay, even though there are some movements, whether we need to turn it on or off during the daytime. So what we did was, little by little, we were injecting more and more inputs, more and more decision making power, and more sophistication into this. So in this case, what really happens is more machines are talking to many other machines, where the complexity or the sophistication of this entire setup becomes higher. So if we talk about the M2M communication, that is one small but a very important aspect of IoT, in the current IoT world, where things get connected into internet. And there are few very important features of this, which are, there are sensors and actuators. There are sensors which are reading something in the physical world, and there are actuators which could be a light, which could be some kind of a maybe a tap or a valve or a gear, which can convert a decision into the physical world. So that's the first part. And then the other part is, to connect these sensors and actuators, there are some kind of a channel connecting mechanism. Those are called connectivity channels and communication channels. Those could be wired or wireless in some way, which facilitates the communication. And the other third important thing is autonomous, where this exchange of information and decision making and actions, they take place without human interaction. So these are the three important things which take place in the machine to machine communication. Well, this is not a new thing, which used to be there for a long time, but this term called M2M was first coined some in 1990s by Nokia, which got widely adopted in the industry all over the place. So then we'll spend some time to understand what are the key elements, or what is the anatomy of machine-to-machine communication. So there you can see one side, there is a sensor, which could be a machine, and in that sensor there is an element of sensing a physical attribute or some characteristics in the surrounding environment. And then that parameter just being sensed can be processed, and maybe processed into a numerical value, or maybe processed into summarization, and probably it can even remember whatever the parameter is measuring. So because of that, it has the processing capability and the memory, and they get transported, the messaging get transported into another machine, which could be an actuator, and to do that communication, there has to be a transport channel or communication channel, and there has to be a transport protocol. So this communication channel could be the cable, or it could be radio frequency, or it could be light, and in some very specific scenarios, even audible voice is used for communication. So in this picture, these sensors for the machines, those are usually called nodes, and the middle part is called the communication channel, and then a sensor can read something, and then an actuator, they can be written into, those are called get and set. But in the real world scenario, there are so many sensors and actuators in this ecosystem. There are certain sensors or certain machines which are able to read things, and there are certain other sensors which could be able to produce some action based on some kind of message which comes into that, and there might be certain other sensors which could be able to process things and have some memory, and there are certain other sensors which might not have any memory, as well as there are certain machines which might not be really sensing anything. Their job is to probably keep an eye on what is going on this communication channel and probably make some decisions and send more messages to take more actions. So this is called, in that case, an M2M network, because there are so many nodes and so many machines in the same communication channel participating into some kind of a use case. And then, so it will get a little bit more complicated. So there are so many machines working in some clusters. Maybe let's say there's a factory in one side and there's another factory in the other side. And there are so many sensors and actuators working on these factories, or maybe houses, or maybe buildings or apartments, and they communicate within a small network on their own. So that's just called a short-range network. So they usually in the short-range network, they can communicate directly with each other locally, maybe with a different set of protocols and different kinds of channels. One simple example is if you are in this particular room, maybe there are computers, maybe there are cell phones, or maybe there are sensors. They are all connected with Wi-Fi, which is a very common communication channel for short-range communication. But in the meantime, if we connect up a couple of factories, couple of buildings, or couple of houses together, then it needs to communicate more than the scope or more than the capabilities of a small Wi-Fi network. So in that case, the communication get transported into another longer range network, and then they goes to a gateway, goes into the other longer range network, and then communicated back into another factory, another house, or another local network. So all these communications sometimes never happen from one sensor to another directly. Many of the times they go to a message hub, and many machine-to-machine communication infrastructures or new IoT infrastructures, they have some kind of a message hub. And what we do is all these sensors and actuators, they get connected into the message hub, and they orchestrate the communication, and they figure out what messages to send from one sensor to another actuator, etc. And also, these message hubs are connected into applications where certain level of decision making and also monitoring and observance can happen. Those are called IoT or machine-to-machine applications, and many times they take intelligent actions as well as providing a machine to human interface. I'll give one simple example. In many of the new buildings, they have smarter energy management systems. For an example, the lamps are connected into sensors, and also the heating and air conditioning could be connected into certain sensors. They all are connected together through some control systems with message hubs. And in the meantime, maybe there might be some interfaces available for even humans to take a look at what is going on maybe mobile phones. So those are the things which I mentioned as machine to human interfaces, which get connected into these message hubs and applications. But before going into any further, let me discuss a little bit about the historical aspect of machine to machine communication, which is not very new. This had been there at least for the last half the century. So some people say that machine-to-machine communication started a long time back, even in the Second World War, because apparently the Russian forces have started certain traps and automation using very rudimentary machine-to-machine communication within their war strategies during the World War II. Sometimes for ignite explosives, sometimes intelligently monitor the movement of other forces. there are certain records that they have used that, but unfortunately it is not well documented or regarded as formal machine-to-machine communication. But on the other hand, a very formal and a very common example where early machine-to-machine communication was used is weather balloons. So in that case, they have used telemetry for data gathering using weather balloons, and the communication had been predominantly one way from the balloon to a ground station. And again, the thing is, this level of technology, which is a big thing by that time, was available probably for governments, probably for academia or some larger organizations or businesses where they could spend a lot of money, and also they have resources as well as they have specialized people to operate this. But the point is, this topic had been very old. It is not new, and the evolution has started over 50-60 years back earlier. But something interesting happened in the 70s. An engineer called Theodore Paraskevkos, who was working in Seattle, came up with a very interesting device called the caller identification device. And I think we all know what CLI is. Sometimes we don't even care what CLI is, because we get the phone number when someone is calling on our mobile phones automatically, and we don't even care about it. But in 1971, this was a big deal, because by this particular box, when they connected that particular box into the phone line, they could really see who is calling and their phone number in it. By that time, this was groundbreaking, and originally they say they piloted this in the Boeing facility in Seattle a long time back. So why is this really important? Because this is the first time that someone used a machine-to-machine intelligent communication through the regular telephony network, which made a whole lot of new use cases possible. So Theodore understood this is a really important concept to be used in many other use cases, and he started a company called Metritech a long time back. And then through that company, he was expanding this concept using telemetry as well as remote control over telephony lines into many other different use cases and many other domains. So some of them had been alarming, and utility metering. Of course, utility metering is something that we are talking right now, but in United States, long time back, they had been using in certain specialized cases utility metering and machine inspection using the telephone lines, and then finally evolving into industrial automation and also into maintenance scheduling. And also the other alarming aspect had been used especially in forces and also civilian safety, dispatch and safety monitoring, especially in the police and all. So for law enforcement, dispatch police forces depending on certain triggers, as well as fire management, gas and water automation management, issuing alarms as well as issuing maintenance issues. This concept of machine-to-machine communication and controlling something remotely, monitoring something remotely started getting widely used. So people say that it is the birth of M2M communication in the commercial space. And then there was a problem. If I go back to the previous slide, so people understood, business understood this a very convenient way of automating certain things, and they started coming up with their own ways of implementing machine-to-machine communication, and even started industrial automation using connecting machines together with their own ways of communication mechanisms and standards and the protocols. But the problem is how to get them integrated together or how to interoperate. There had been a huge issue because everyone had their own standard. So that's where the standard called SCADA came in. So that is called supervised control and data acquisition. This is the first standard came in this domain, especially for industrial automation, which is a very, very mature standard with various a series of different level, field level, and also plant level, production control level, and finally production scheduling level. With these levels, they came up with various standards and protocols to communicate, as well as what information is communicated in which layer, as well as what are the interfaces for these layers. So if you see this particular toll machine, that is one of the very, very early SCADA consoles which is being used. But now it is very, very different. SCADA had been evolving over half a century, and then the standard is so mature. Even today, with some of the very high-end machine automation or industrial automation using PLCs and all, this standard is being used as the de facto standard. And even ranging from small factories and even to the International Space Station, they are all controlled with the same protocol or the standard set called SCADA. So why is SCADA useful? Because even the very new concepts in IoT, they are all based on this concepts, probably not the same standards. Standards are very different and they are modernized now, but at least in a very fundamental level, the concepts are being borrowed a lot from this particular standard set. Then some very few important things happened in the 70s, 90s and 2000s. One is the telephony network deployment in a wide way in many countries. Obviously by 70s, most of the Western nations, they had the telephony network deployed in big way. Most of the domestic users as well as the business users, the telephone network was widely available. And in the meantime, in the 70s and in the late 80s, it became standardized and widely available in countries like us as well. In 1980s, there was a really big boom in the telephony industry in Sri Lanka too. So with that, in addition to voice communication, there had been an opportunity of communicating data, communicating control signals, and remotely monitor something and also remotely control something. And the important fact is, by that time, those communication had been mostly point to point, from one point to another point, using something called a modem. Many of you, I don't know, nowadays do remember what the modems look like, but there were bulk equipment which we connected into a computer, and both sides we got the computers connected through modems. And then most of the communication protocols, some of them have been proprietary, some of them are getting standardized, and those modems were used over the telephony network before the PSTN network with cable and RF, but with the PSTN network, we came up with a standard, and then the reach as well as the affordability became very, very realistic for even small scale businesses to use machine-to-machine communication. So after 70s, with the PSTN deployment, what happened was there was this affordable shared network with widespread access to implement use cases with communication. That was the groundbreaking thing which happened in the 70s using the PSTN deployment. But in 90s, another revolution came up. That is the widespread availability of the mobile network. So then, some of the constraints that we had with the telephone system was being able to overcome using the mobile connectivity. One is we could have expanded coverage, and many subscribers which who did not have the opportunity of connecting into a wired line had the opportunity of getting connected into a radio based mobile line. And then the other important things, the mobility. Of course, there are certain use cases where you can't have the modem fixed into a wire because certain things are moving. For an example, maybe a truck core, maybe a person who is dispatching certain equipment or certain goods. Those things are not stationary, those keep on moving. In that case, mobile use cases made possible because of the cellular technology. And also the other important fact is the cellular technology kept on evolving so fast from the first generation cellular to 2G, 3G and now 4G and 5G. With those advances, a very large number of devices can get connected into the mobile network with ease. Again, that made a lot of use cases much more realistic than using the telephone lines. And in the 2000s, another important thing happened, which is RF as a commodity, which is the ability to simply buy a SIM and get a communication mechanism enabled rather than building our own things. Okay, and sometimes back, I remember a long time back when I wanted to create a simple control circuit. Oh my God, I spent so much time to, first of all, I created the radio. We used to really turn our own coils, create our own radios, and get a very rudimentary, less reliable and very primitive radios working for a short range. And we spent weeks to get the, first of all, get the radio link working. And after the radio link is working, then we spend so much other time to get the real use case built, again by soldering the equipment together and getting circuit boards done by ourselves, and so much work. Right now, as of today, we don't need to do anything. In 2000s, what happened was you could simply buy a radio modem where you can insert a SIM and get it working, and then connected whatever your use case into that, and within weeks you could get it up and running, or maybe now, as of today, within days, you can get a simple prototype done and get a use case worked. So with the invent of low-cost modems and with the ability of really connecting things in the licensed and free spectrum, both short range as well as long range communication was possible. And also with this advances in the mobile technology as well as other RF technologies, not only the range but also we can communicate with very low power from one point to another. So that is another aspect which revolutionized the M2M communication nowadays. So let's take a look at one of the modern IoT node which is capable of doing something useful as well as communication. So most of the new modern IoT nodes which you can purchase for a very low price or reasonable price, they definitely have the radio access. Radio access means ability to communicate over radio channel, and sometimes it could be short range communication channels like Wi-Fi, Bluetooth, or even Zigbee. And or it could be long range communication, even connecting into something like LoRa or even GSM over the mobile network. It has their own computing power and it has their own memory, and they are low power, consuming very low power, so that you can even power it up using batteries. And then also it has the capabilities of integrating with analog and digital interfaces, which makes us easier to measure things either analog or also digital. And also they can be location aware. For example, whenever you can really connect a small GPS antenna, we can accurately pinpoint exactly where you have deployed this particular node or the component. And these set of capabilities were so much expensive long time back, probably maybe definitely about 3 years, 4 years back, those were ranging from hundreds to thousands of dollars. But nowadays, these capabilities are available for a very less expense, maybe a 2-digit number, rather than spending so many dollars to get all these capabilities in one shot. And then let's see where this machine-to-machine communication is applicable in our day-to-day life. So one thing is production automation. There are various standards like SCADA, DSL, and BPL being used in production automation. So in agriculture, where they really use a lot of measurements on temperature, measurement, light, humidity, water levels, etc., and moisture, as well as controlling the light conditions, controlling the humidity. They use technologies like LoRa, they use cellular technology, and also they use DSL. And in some other countries, especially much larger countries, which I'm fairly exposed in Australia, they use machine-to-machine communication in big time in monitoring and surveillance, because in much larger countries, monitoring the assets and the infrastructure is a big issue, and it's a very complicated problem. So in that space, machine-to-machine communication is very, very widely used, and they use again DSL, cellular, and LoRa to do that. And then the other thing is, I think many of your vehicles are a very sophisticated mini machine-to-machine network. I think probably that is the most dense machine-to-machine network that you can ever find in a very confined space, with maybe if not tens but hundreds of sensors, and so much computing power, and so much actions take on the data being collected. For example, I think very simple example is hill assist. When you stop your vehicle and push the brake pedal in a hill, what happens? So it waits for 5 seconds to see whether your brake pedal is pushed. If it is more than 5 seconds, it understands we are in a hill, and it detects the tilt sensor. You get another measurement and decides that you are in a hill, and then what happens is it is activating your parking brake automatically until another 3 seconds, right? So in that case, you won't slip down. So this is a very simple example, but there are so many, probably thousands of use cases in a vehicle compacted into a very small space with the machine-to-machine network. And building automation, so with a lot of not even smart cities, but even fairly small houses and apartments, and also industrial buildings, there are a lot of building automation is happening at the moment to conserve energy as well as to improve our lifestyles. And Wi-Fi, BLE, which is Bluetooth Low Energy, and edge computing are a series of technologies used on that spectrum. And by the way, this is a very unlikely example where machine-to-machine communication is used so much, but we are not, which is not very visible. In entertainment, they use certain standards like DMX and MIDI to orchestrate the entire scene, as well as control the lighting, music instruments, and various other entertainment aspects in the stage. Also in our day-to-day life. Now, I think I think most probably many of you might be aware of your digital assistants. Maybe those might be running on your phone, as well as those might be running on devices like Google Assistant or Amazon Dot, which uses again Wi-Fi, BLE, and a series of other standards to provide a different level of lifestyle and getting things automated around your life. So, so that is a very high-level introduction about the history of machine-to-machine communication, and also what are the use cases where this extensively used. So let's spend some time now to understand where machine-to-machine communication fits into IoT and the bigger picture. And in that case, Let me explain how exactly M2M communication fits into the bigger world of IoT. To talk about that, we need to talk about what IoT is. IoT is obviously, as you might know, those are called Internet of Things, which is a probably a bit of a decorated word and maybe a commercial word, but essentially those are various sensors and other actuators working directly connected into the internet and talking to each other. But there are some important things that I want to categorize separately and talk about. One is, in the internet of things, there are in that corner there are big things. The big things are things like maybe vehicles, or maybe certain ships or vessels, maybe robots, or maybe gas pumps. Those are bigger things. Why are they called bigger things? Usually some of them might be stationary, some of them might be moving, but they are bigger and they can afford to have bigger processing power and a lot of sensors and ability to remember a lot of things, and also to do a lot of computation and making decisions within themselves. That's why these are called bigger things. These are usually large and these are called not constrained, which means they have ample resources in terms of computing, storage, as well as power. And also the second category is the small things. Small things are usually small and those are constrained. What you mean constrained are they are not very rich in terms of the computing power it has, as well as the other resources as memory or even the available energy or power within them. So usually those are little things like certain sensors which you mount maybe on the wall or maybe in the ceiling, and maybe in a wristwatch which is monitoring your heartbeat or whatever, operated by battery. So those are called constrained devices. Those are small, not so capable, but plays a very important role in the ecosystem. And then the third aspect is again different. Many of these big things and the small things, they talk the language of the internet, which is the IP protocol, which means they can get connected immediately into the internet and they can talk with something else which are in the internet. But there are certain other things, they don't talk the language of internet, they don't communicate with the IP protocol, and those are called non-IP things. They can't talk the IP language or IP protocol. Those could be small or those could be constrained devices, and they cannot get fitted into the internet very easily, so they need some help. So that is why there are certain things called gateways in between the internet and then those devices to translate the language from non-IP protocols into IP protocols. So somehow all these things get connected into the internet, which is in the middle, somewhere here, and they can talk to message hubs, and then finally they can talk to IoT applications, and finally they can communicate with each other. But the point what I'm trying to make here is, depending on these big things and the small things and also non-IP things, the machine-to-machine communication standard can be different. Because with the same protocol set or the same standard or the same mechanism, they cannot become optimized in communicating. So that's the next part I'm going to arrive at. So let's again think how these devices get connected into the internet, and what do they do, what is their responsibilities, and also who does what. They essentially do three things, all these participants. It could be the things, it could be the applications or message hubs or gateways. They do messaging and they do processing and they do something else called device management. I'll explain these things a little bit later on. So if I go into the things, mainly they do messaging, they can read something, or they can write something, or which means they can take an action on some message. Those are called messaging activities, that the things do. And also they can do few other things, like when they don't do some work, what do? The best thing to do is sleep, because if they are sleeping, they can conserve energy. And then also they have the ability to configure themselves. Also, sometimes they need to be updated once in a while with better capabilities on your parameters. So those are called over-the-air updates. So these final later three things called device management, but the top two things are called messaging. Those are the things that the things do. And then these things sometimes can talk to the internet directly, and sometimes they cannot talk to the internet directly. And when they can't talk to the internet directly, they need to be helped and assisted with a gateway to translate the language. So these gateways, they do protocol conversion and also change the structure, as well as they do the diagnostics and sometimes do repair things, provisioning, and sometimes when things go wrong, they do alert things as well. All these things are done by the gateways. And then the message hubs, their responsibility is to deliver messages. When one device, if I want to deliver a message from myself to another person, these messages all the way go through the message hub, and they figure out how to deliver that into the next person. That is their primary job. So message delivery, and maybe delivering a message to a group of devices, and also transforming one format of a message into another format, and also to deal with security. That's the job of the message hub. And then finally, the IoT applications, they usually provide a machine to human interface, and also they, based on the data which is being gathered and communicated, they can do insights, and also they can do analytics, and also they can provide some rules, apply some rules, and automate certain things based on the rules, and also they can do provisioning and firmware updates. So in order to do all these three types of things, the machine-to-machine communication, we need to pick different types of communication for different use cases, and there are certain deciding factors. So one deciding factor on your left hand side is the length of the communication. If it is short range, you need to use one technique. If it is long range, maybe we need to choose another technique. And also we need to think about whether these devices or the machines or the sensors, are they constrained or not. If they are constrained, which means they have lower abilities, the power consumption, computing, and the memory, then there are different ways of communicating with the constrained devices. If they are not constrained, of course, then we don't have to worry about them. We can use maybe a much more different or much more cheaper way of dealing with them. And also whether it is IP or non-IP. If they are IP, yes, there are certain communication methods that we need to use. If it is non-IP, some other. So based on these three deciding factors, we need to choose a data format, and we need to choose a communication protocol, and also we need to choose a different kind of a data link to connect them together. So data formats, those can be human readable or probably not human readable, and the communication protocol, those could be message based or session based, those could be read write, or also they could be able to manage things on a device. And in the data link, those could be wired, or this could be wireless. So sometimes these links can be dedicated between two parties, or probably it could be shared in a network so that a lot of people are sharing the same data link. And also data link can provide certain level of bandwidth, and also they might have certain latencies. So all these factors we need to think about when deciding these parameters. So let's start with the data link. So data link is usually some kind of a medium for data transfer. So in a data link, this medium is created using a few components. In the middle, you have some kind of a transport medium, which could be electric, or which could be radio frequency, or which could be light, or maybe even in some case which should be sonic. Or anybody who have heard about using sonic or sound for machine-to-machine communication? Yes. Excuse me, sir. Can you explain where we use them?
We have used it on an experimental base for indoor machine communication. But really application by test application.
Okay. Yeah, I think. Sorry, sir. Go ahead.
Yeah, so the reason we use that is we want to interview with other radio communication. Because of that purpose we have.
Correct. Yes. Yeah, in some use cases where certain mediums like wireless might not be viable or radio frequency might not be viable. Few examples are highly radioactive environments, as well as certain environments with a lot of electromagnetic noise. Sometimes we need to tend to use certain other mediums. So one common medium is light, and wherever light is not possible in certain cases, especially in nuclear facilities and also with certain specialized military applications, they also tend to use a very unlikely channel, which is sound. So either way, with this medium, in both sides, usually there is a transmitter receiver, which is connecting the consumer, both the sides consumers, to communicate with this channel, because ultimately if I want to communicate some of my thoughts as a consumer to another individual, then obviously definitely there is no way to really transfer my thoughts directly to another person, because we have not yet implemented telepathy just yet. So there has to be a way of really transferring or converting my thoughts into another format, which we usually do by converting them into words and either verbally communicating or writing them in a piece of paper and transferring the paper. That is exactly what this transmitter and receiver do. They convert whatever the message that the consumer has into a format which can be communicated over this medium. So there are various transport standards. What I do is I'll not go into the details right now. I'll share this deck with you. But there are, for different purposes, there are different transport standards. Some of them are wired and some of the others are wireless. And some of them are short range and some of them are, the others are long range. And both wired and wireless communication are used both for short range and long range communication. So then the second aspect is the protocol. So earlier we discussed the channel, and now the protocol. Protocol is using the channel, what exactly or how exactly we communicate, or the language, the words and the sentences and the paragraph that we communicate. That's called the protocol. So that's a common agreed format with two of us. We both agree and understand, so that we can encode and decode our information with the communication. So there are a few standard protocols which are widely being used in M2M communication. I cannot really say all of them are protocols, but in the commercial terms, these are considered as protocols. One is HTTP, probably the most known and the popular format of communication in the internet. So a lot of unconstrained devices, and in quick, dirty prototyping, we heavily use HTTP as the preferred way of preferred communication protocol. By the way, the second most widely used protocol in the industry is called MQTT, which was originally developed by IBM and now managed by a group called Oasis. This is highly used for sensor communication, especially with the constrained devices, because this protocol is a message-based asynchronous communication and event-driven communication, which is very, very efficient, small and lightweight, so that even very small, constrained, low-power devices can use effectively. By the way, MQTT, even though it is very highly used and widely used today, is a very old technology, more than 40 years old, originally developed by IBM. But recently, especially in the mobile and the telecommunication sector, when they got involved heavily on IoT, they came up with some modern techniques or modern protocols. Some of them are CoAP, that is called Constraint Application Protocol. This is becoming the de facto standard in many new IoT devices and M2M communication. But that is only for communication between two consumers. The other protocol, which is again gaining momentum, is called lightweight M2M, which is again used for sensor-based communication and also in devices and gateways. The additional advantages, in addition to messaging between two parties, this is also able to control and manage the devices. For an example, with this particular protocol, if I have a sensor in my hand, not only I can communicate with this sensor, but also I'm able to make a firmware update and upgrade the device. And also, if I think, okay, this device has to be turned on and turned off in a certain schedule, I can also manage that. And also, I can even monitor whether it's operating properly. Also, maybe there's a security threat, someone has hacked the device. In that case, I can also detect that and I should be able to deprovision and destroy it remotely. So those capabilities are available in this protocol called lightweight M2M. And the two other protocols called OMADM and TR-069, those are also being used, but more than in the consumer space, it is heavily used in telecommunication sector and mobile sector for specialized functions. And then if I do a very simple comparison, because as I mentioned earlier, this M2M communication uses different protocols for different purposes, and selection is based on certain parameters, based on the overhead and based on the footprint, and also the kind of server load they are making, as well as the data model that they communicate, firmware updates, device management, response time. There is a whole heap of different parameters considered when selecting a protocol for this. So this shows you the comparison between those different protocols. And also functionality wise, some of them are push, some of them are pull, some of them have the capability of really discovering the sensors and figuring out what is the sensors available in the network, ability to boot, ability to reset, and also to perform diagnostics. Like that, there are a series of attributes available here. Some protocols do well in some of these, and some others are not applicable. So based on that, we need to make the selection. And then the other thing is, very importantly, the data structure or the data format. In M2M communication, this is kind of the syntax, or this kind of the spelling that we use to communicate our words. So there are three very widely used formats. One is XML, probably the oldest, and the other one is called JSON, which is heavily used at the moment. And there's another newer format called SendML, which is gaining momentum, which is specially designed for machine-to-machine communication and reading sensor data. So these formats, they define the grammar or the structure or the semantics of a message. And by the way, these are certain standards, but there are so many numerous other structures and formats available which could be proprietary, used against the industry, because still the industry in this area is maturing at the moment. There is no de facto or widely agreed standard. So these standards are at the moment competing with each other. But I think right now, as we speak, JSON and SendML are gaining momentum. But if we come up with an application or new use case, how do we choose one? That's the question. So I'll give you a very simple example. Let's say we create a electricity meter, which is communicating the electricity consumption in a household or in a business, maybe every half an hour. So this is a format that it is communicating the electricity consumption in these three formats. So as you can see, if you use XML for this use case, it is using 103 bytes. If we use JSON, it is significantly lower, it is using 247 bytes. But if we use SendML, it is even cut down into 218 bytes. So same information, same thing, same message to get communicated. With these three formats, as you can see, it consumes different payloads or different data consumption over the channel. So that is one aspect we need to consider. By the way, out of this, there's another factor. Machines are reading these things, but sometimes it is so convenient for humans to be able to read them as well. Sometimes, of course, we do diagnose things, and in that case, when you troubleshoot things and when you want to understand what is going on, it is, as long as it is easy to read and understand, it's an advantage too. So out of these three things, which is most readable? Well, it's a personal preference, but definitely for me, at least, the middle one is more readable and easy to understand. So that is another factor. Like that, there are different factors that we need to think about choosing the format. So putting all these things together, this is one example where these links, protocols, and also channels work in the big picture. So in the Internet of Things, you can see in this side, there could be certain sensors which are connected into a cellular network over 3G, 4G or 5G, and they get connected over RF mobile protocols, GSM, and then over the cell it can communicate into some application over HTTP or MQTT or some other protocol. And there could be another scenario where we have a bunch of Bluetooth sensors, for an example, temperature sensors, and maybe alarms, the door sensors, window sensors. Those usually work with either Wi-Fi or maybe nowadays, as long as they are battery operated, mostly with a protocol called Bluetooth, a technology called Bluetooth Low Energy. So those get connected in a very small space into a Bluetooth Low Energy gateway or cellular, and then they can get communicated over the internet with OMADM. And then in agriculture sector, where sometimes you don't have wires and sometimes you don't even have a mobile network in a very remote area, again getting maybe the greenhouses or cattle or animals connected into the agriculture network, they heavily use LoRa as a technology. So in that case, sensors get connected into a LoRa node, and then the LoRa node can communicate, the concentrator can communicate over LoRa into another gateway and then back into the internet. And finally, they can get connected into various applications, data analysis, dashboarding, mobile apps to control them, and even artificial intelligence to derive certain facts big time through the internet. So lastly, I will go through with a few aspects of what is going on recently with the latest developments in the machine-to-machine communication. So in cellular data link, the evolution of that had been a big deal over the years, because more and more a significant amount of machine-to-machine communication is now shifted over the wire into mobile networks. And then in the early days, we used the CDDP or TDMA as the early cellular technology. And then with the establishment of 2G, technologies like GPRS and it were used. And I don't know whether anyone remembers how we used GPRS, which is a very, very low communication mechanism. Yeah, it takes ages to come up with a web page, but still it used to be a big deal by that time. And YouTube was not possible with GPRS. Then it came 3G, which is powered by CDMA and HSPA. So with 3G, the whole thing was converted into a very high bandwidth channel. So with that, use cases which consumes a lot of data was made possible with this. For example, a lot of surveillance and video monitoring went into 3G, went into the mobile space with the invention of 3G. And then with 4G, another important thing happened, which is narrowband IoT. As an organization, we work a lot with narrowband IoT. There are a few standards called CAT-M1 and CAT-NB1. Those technologies made some incredible things. For an example, if you take a cellular tower, with one cell you can go up to about 1024 sessions, concurrent sessions. So which means the number of sensors which can communicate concurrently with one cell is limited in a particular area. But right now you can't deal with this. The reason is even with one cell, if you want to monitor your electricity or water consumption, or maybe your numerous number of household sensors, 3G or any other technologies can't simply handle it, because there are only so much concurrent connections are possible with the traditional mobile network. With narrowband IoT, what happens is rather than sacrificing the main band of the cellular spectrum, it is using certain sidebands and providing that dedicatedly into machine-to-machine communication. There's a flip side, which is you can't do a lot of fast, high bandwidth communication with those sidebands. But most of these small devices, they don't consume a lot of bandwidth unless you are doing something like video surveillance. So most of the devices, they process information and send a small tiny message, maybe less than half a kilobyte, very quickly, not very frequently, maybe once in half an hour. So those kind of communication can be very well done with this new technology called narrowband IoT. And the good thing is, with the previous technology, yes, one cell could handle up to 1024 channels, concurrent connections. But with this, it can go up to probably more than 120,000 concurrent connections by one cell, which is incredibly high, maybe 100 times higher than the previous cellular technologies. So that is why narrowband IoT was purpose made for machine-to-machine communication in IoT, which is a big breakthrough. I think about 1.5 years back, many of our major telcos, both Mobitel, Dialog, they created the narrowband IoT network and deployed that in Sri Lanka too, which is happening very widely in other Asian countries as well as many other Western countries. And the other important thing is that narrowband IoT will be part of the 5G standard. So because of that, any applications that we design today with those two technologies will be applicable even in the 5G standard. Second aspect is the way we build things. If you take a look at the picture in the left-hand corner, that is the way we build things long time back, maybe 10 years back. This is how we got things started. We had to build our own circuit boards, and we had to really solder everything by hand, and we had to burn the firmware by ourselves with very rudimentary techniques. Life is interesting, but it was very hard, quite honestly. So the problem was to come up with a small use case, to come up with a prototype or a proof of concept. It took so much time because we were meddling around with so many things like that to come up with even a small thing working. But maybe in the last 5 years, things got dramatically changed. And right now, rather than really building our own circuit boards, our own little computers, and also our own communication devices, what we do is we assemble things. For example, in the middle picture, you can see a computer board connected into some daughter boards with some sensors as well as a radio unit, which you can purchase very quickly if they are available in the market, and then plug them together. All of a sudden you have the computing power, you get some sensors connected to it, and also maybe insert a SIM into that radio module. Well, you are connected into the internet and your use case is done. So that is a really good step which happened in the last 5-6 years to make things or build things in a much rapid way rather than starting from the scratch. And the other thing which happened in the last 2-3 years is this. Basically, the companies like Microsoft, Google and Amazon, they started providing the connectivity infrastructure, message hubs and also protocols directly as a service on their platforms. In that case, we don't need to really put up our own server, configure our message hub and really meddle around with things. We can simply go to AWS, Google or Microsoft and then create an IoT hub service, configure a few things and get our device connected to that. So basically configure and use. So the bottom line is, the way we build things, the way we prototype things, and the way we really get something to working, that was changing dramatically. And well, that was changing for good, because we can do the prototyping much faster and much more conveniently, as well as some of these prototypes that we do are much more reliable, because those components and the software configurations and the services are tested by others so many times. So we don't need to worry about really testing them and fabricating them on our own. Well, the third thing is how we deal with power. And many of you, how frequently are you charging your mobile phone? Once a day? Like something like once a day, right? Okay. Long time back, how many of you remember that big brick size mobile phone? Okay. How long we were charging? We had to pretty much connect it into the power all the time, and with a couple of hours of use, it drains the battery. By the way, charging or replacing batteries in some of the new devices, we can't afford that, because those are heavy maintenance. And the expectation now is, you fabricate something, you put on some batteries and then let it run for years. That's the expectation. So if you want to do that, the subject called power management has to be so advanced. So there were some new developments in those areas. So number one, passive or active power harvesting. Power harvesting is, of course, there might be batteries, so there might not be even batteries. Rather than having its own energy source, are there ways of really creating its own power by the energy available in the atmosphere? In some cases, it's possible. One very simple example is, maybe you might be using a simple access card, which you use, the RFID access card, which you use for checking your attendance. Those access cards, they have a RFID chip inside it. And are they battery powered? No, actually they get powered using the radiation that they use in the wireless communication between the reader and the receiver. So they create power with induction. So that is a way of really passive power generation. And there are certain other elements with piezoelectric principles. You can create power with motion. So some of the very tiny use cases, sometimes there are devices which are harvesting power with the movement, and with the movement they collect a little bit of power and they store it. And then the most obvious examples are with solar, and then with the differences in heat, they also can create power. So with all these things, there are certain devices and use cases which are possible to run with less batteries or even no batteries by having its own power source. And then the second aspect is power management and sleep management, which is figuring out when to use power, and while using power, what's the most efficient way of really using power, as well as when there is nothing useful is happening, how to turn off myself and maybe get into sleep and conserve the energy. So most of the many of your mobile phones, they have a very specialized chip called power management chip, which is taking care about the optimal usage of your battery. And one good example is, I don't know whether you have felt over the time when we use your iPhone for 4 or 5 years, if you have an iPhone for a long time, I don't know whether you might have felt that slowly the iPhone gets a little bit slower with no reason. But your battery is fine, you can still use the battery, charging once per day is enough, right? What really happens is, intelligently it is figuring out the status of battery, it is slowly lowering the clock speed of the main processors so that it is not consuming the battery that much. So actually what happens is the battery is decaying, but it is just imitating like, okay, battery is fine, but what really happens is the processing becomes low. So not only in the mobile phones, in many IoT applications, the battery management is a vital thing. There are specialized chips that we use for battery management. And then the other one is the advanced polymer batteries. Sometimes back we were using technologies like nickel cadmium, and also nickel metal hydrate. And now we are using a lot of lithium batteries in our use cases. And recently we are using specialized lithium polymer batteries. Those are newer battery technologies which are much more efficient and also much longer to use, as well as affordable too, so that our solutions are economical. Very recently, actually last week, there was an announcement of a new research from a joint venture between UK and Australia. They are designing a infinite edge battery, especially for very small sensors and even things like hearing aids. A battery which will never die. Basically what they're doing is they're using nuclear waste graphite with nano very thin wafers of diamond to come up with a virtually infinite lifetime for a battery, which could be available for very different use cases. So maybe if I'm using my hearing aid, I need to be careful about the radioactivity, but they'll figure it out. And finally, all these M2M channels, they use some kind of a communication technique, especially if it is RF. They use low power radios, and over the time, compared 5 years ago, most of the RF radios that we use are very efficient, and they use different techniques to minimize the power consumption in the way that they communicate over the mobile channel or whatever the RF channel that they are dealing with. Other aspect is dealing with very short distances. Of course, in short distance, short range communication, there are different technologies and standards that we use. If it is centimeters or very close by, we use NFC and RFID as the channel. or the communication technology. But if it is meters, we use some other set of technologies like Bluetooth Low Energy or Wi-Fi. These developments in these technologies actually made automation really possible in the consumer space, because a lot of consumer grade applications are using these 4 technologies as the main communication channels. And then dealing with the long distances, of course, there are so many different technologies which are able to communicate over the kilometers, maybe a couple of kilometers, so maybe hundreds of kilometers, so maybe even more than that. In the cellular space, NB-IoT and LTE-M are the predominant technologies for machine-to-machine communication in the licensed spectrum. In the unlicensed spectrum, LoRaWAN and Sigfox, those are the dominant standards. And there's a new, very new technology called long-range Wi-Fi, which can have transmission power up to about 1 to 2 kilometers. So with that, there are some specialized use cases where we can use Wi-Fi for even kilometers. By the way, all these things, we need to have some kind of infrastructure, maybe Wi-Fi network and maybe a mobile network, a LoRa network available in the area that we communicate. But there are certain areas where we don't have economically viable communication channels. A few examples are, there are very rural areas where agriculture happening, or maybe research happening, maybe wildlife research happening, which has no access to whatsoever the communication method. So the other area is pole exploration, Arctic and Antarctic areas where they have various sensors which are dealing with measurements with climate change as well as habitat, and also decaying of ice, etc. So they were largely dependent on satellite communication, which is very expensive long time back. But for M2M communication, something interesting happening right now, which are called low orbit cells. So basically what they are mini mobile networks or mobile cells, but fitted into some tiny satellites hovering in a very low orbit. What happens is, if I get a satellite in my near vicinity, for a fraction of time I can create a mobile connection with a satellite. So there are a couple of companies who are working with. Some of the companies are in US, and there's another joint venture happening between Australia and New Zealand on another network like that. And with this network, we can create a small sensor or an equipment. It can keep on reading about something, keep on storing, but there will be 2 windows per day where you can have a communication channel for about 1 minute. So you just need to keep on waiting until that 1 minute comes, and then you can establish the communication, transmit everything, update everything within that 1 minute and go to sleep. So that is becoming a viable another alternative to conventional satellite communication. And then the other aspect is dealing with latency. And why does latency matter? So any channel, any communication channel on machine to machine, it takes time to get a message delivered from one end to the other. Obviously, if we use wired communication, obviously it travels pretty fast within milliseconds, and obviously most of the standard is hundreds of milliseconds, and that is good enough for most of the communication. But of course, if you use satellite communication, the latency is a little bit worse than that. I think it takes around 500 milliseconds for the entire round trip over the air, as well as the latency in the equipment. So for certain use cases, this latency is not a big deal, and if I'm reading water meters, so if I'm reading energy consumed over the power meters, as long as somehow I can get them delivered in a couple of hours, and if they are updated in my statement in few hours, things are fine. It's not a big deal. So many application latency is not an issue. But think about another critical application, which is maybe entertainment or communication or maybe surveillance. There you need to have very real-time updates and monitoring. In that case, the latency in seconds is a normal. You need to have better latency than that. But with the most up-to-date communication mechanisms, even with mobile communication, the latency is in hundreds of milliseconds. Think about real-time surgical operations, which is already happening in the world. For an example, the surgeons and the physicians in one continent might be going through an operational procedure or a surgery on a patient in another country, another continent. In that case, already there are equipment and there are surgical equipment where the surgeon can control the robotic arms and perform the surgery real time on a patient. So the milliseconds of latency becomes life and death kind of a situation in a situation like that. And, almost real-time latency, the speed is required in a use case like that. So there are different solutions for it. So one solution is there are technologies like 5G which are promising to deliver that kind of latency. So they have reduced the latency from hundreds of milliseconds to about theoretical 36 milliseconds on 5G networks theoretically, but in practical terms they have tested in many countries. 5G is promising to deliver about at least 80 to 100 milliseconds, which is fairly good enough for many kind of real-time use cases. And the other thing is, okay, if it is taking time to go over the internet and communicate with a lot of things, okay, why do we communicate in the first place? Rather than really going over the internet, make those decisions and make those, apply those rules or whatever the processing, do it locally. For an example, let's say we have a lamp here and we have a sensor here. Why do we really want to communicate those readings in this sensor all the way to another place in the internet in a server and then come back and turn on the light? We don't need to do that. So rather, if you want to have almost real-time experience, keep the server down here and communicate locally. So that is where a concept called edge computing comes in. In that case, a lot of decision making, artificial intelligence, the real-time processing and intelligence, which can happen in the cloud, are taken to a local server or something called the edge computer, which is situated locally, and processing happens locally. So these are the different ways that we can deal with the latency. So with these different aspects, I was talking about the evolution of the cellular data link, and also how the way of building was advancing, and also how dealing with power got improved, and also how we deal with the short distances, how we deal with long distances, and how we deal with the latency. With all these things, we have a very different combined effect as of today, which means the entry barrier to prove some technology has really gone down. For an example, if we have a concept, if we have a use case, and if you want to try it, it has become much easier now than what it used to be 10 years back. So a lot of things that we want to have a proof of concept, we can easily do it now in days, and rather than spending weeks or months compared to some times back. So what does it mean really? So this is opening up a lot of opportunities for entrepreneurs as well as public organizations and many other industries. And the other thing is that the application scope, which means sometimes back I told you the telemetry was being used in some certain things like weather balloons and also remote weather monitoring, very small and confined sort of use cases. But now these applications are all over the place. We can apply these technologies to many things that we can ever think about in our everyday life, because so many possibilities are there and the constraints are lesser. And also, with the aspect that I told you, the time to market has become lesser once we get an idea to convert that concept into some tangible product. Thanks to all these advancements, it is much more rapid. So in that case, we can convert the idea to the market much more rapidly and take it to market much more faster. Those are the good things. And there's a flip side as well. The final point, because these technologies, standards, and all these good things are ever changing and becoming more and more advanced, what happens is anything that we build today, there's a risk of becoming obsolete in a very short period of time. So which means upgrades. And sometimes the frequency of upgrades and the frequency of decommissioning certain older versions without supporting them, it is becoming more and more frequent. So sometimes in certain cases it can be seen as a negative aspect as well, but overall the combined effect is much more positive, while we have certain negative aspect as well. So finally, to end the conversation, what I wanted to point out is there are so many different applications. Whatever the industries that we are working with, whatever the domains that we are working with, and whatever the businesses that we are working with, there's a very high possibility that some aspect of that will be improved or made into a much beneficial business case using IoT, using machine-to-machine communication in very different spectrum of things. And even within our country, for Sri Lanka also, we have an advantage because unlike some of the larger countries, we are much more agile, and the development is much easier than some of the larger countries, because the cost of change and the cost of infrastructure is so much bigger in some of the larger countries. So we definitely have an advantage of using these technologies in anywhere that we can think of compared to some of the other countries in the world. So with this session, what I wanted to mention was how machine-to-machine communication has evolved from very rudimentary and fundamental form into something very much sophisticated in the recent past, and how it evolved and what are the standards, and also what is the anatomy of that, how they form together, and then finally how this machine-to-machine communication is applied and fitting into the bigger world of IoT, and then what are the aspects that we need to think about in choosing certain technologies and methodologies, and then how they impact the current world as well as how it will impact our lives and our professions as engineers in the current world, in a summary. So thanks IESL for arranging this, and in the meantime I would like to open up the conversation for any questions.
Thank you for something. So I want to ask a question in relation to the horizontal technology.
Yeah.
So how do you discuss your communication in 5G technology application, and so how do you predict the growth that you can have in terms of 5G?
Okay. I think That's a very good question, and also a very hard to answer question. The reason is there are so many things 5G which are not really firmed up still. One is technology, the other one is political. Let me start with the technology side. The 5G is actually not exactly a new thing. 5G is actually an evolution of some of the current technologies into with some fine tuning into a better combination of techniques in the cellular communication techniques. So essentially 5G is addressing a couple of things. Number one, it is addressing the most important factor of the bandwidth, which means how much data you can communicate in a short time. Which means if we are talking about 10 megabytes per second today, so 5G might be talking about 100 gigabytes, or maybe even 1 terabyte, something like that. So amount of bandwidth that you can communicate over the same spectrum with some tiny tweaks into the techniques that we use, both in the handset of the devices as well as in the communication cellular technologies. That's number one. Number two, with certain tweaks, they have been able to really reduce the data propagation delay and reduce the latency with a series of magnitudes. So I think the trump card is 5G offers you high bandwidth and low latency, and with that it is providing you much better user experience, and as well as it will allow you to consume a whole lot of much more rich content over the cellular network. For an example, as a long time back in the GPRS days, YouTube was not possible. Sometimes after that, YouTube was possible with decent, okay kind of picture quality. But with 4G now you can enjoy high resolution HD picture quality using YouTube, right? And maybe with 5G, you should be able to probably even enjoy 4K video without an issue over the mobile network. So that's the promise that they are delivering. But to make that happen, the problem is you need to completely change the mobile network operating system, which means that the network layer has to be changed. The software as well as the equipment has to be changed. And also the cell technologies are different, and those cell technologies are high density, low range cells, which means currently if 4G technologies are powering one cell with a 2 kilometer radius, I think with 5G what is going to happen is it might be covering a very small cell, maybe about 300 or 400, 500 meters with one cell. So which means in the same city, in the same space, you need to embed so many cells. And also these cells are high power, and people are suspicious about high power cells because sometimes I don't want to be sleeping next to another cell in my near vicinity. So because of that, sometimes more than the technology, the social implications are coming in. Okay. And then the other thing is 5G technologies are really developed by some rival organizations. They have the competition between themselves, and which has even gone into the geopolitical space of even influencing who will win providing equipment for these 5G. So quite honestly, the short answer I can give finally is it's a complicated topic which has technology and social as well as geopolitical implications, but eventually I think those will get settled and people will have more acceptance. At the moment in Brussels, I believe there's a huge protest against 5G towers by the community, And recently in Melbourne and Sydney, there were protests by citizens. Okay, we don't need 5G. We don't know how it is going to impact our health, etc. I think it will take time to get acceptance, as well as if there are rejections, obviously the companies will have to further develop the technology into an extent that it will have the widespread acceptance. As of today, I think it's a bit of a journey.
Any more questions?
So with this machine-to-machine communication, there will be the network is prone to security threats. Let's say if somebody hacks into our network, they can use our devices to launch a distributed denial of service attack for something like that. So how can we address the security aspects of a network?
Yeah, that's also a very good question. And whether you are talking about a billion-dollar industry, the IoT cybersecurity, which is an emerging subject, which is going to make a lot of money. So the truth is, some of the early machine-to-machine communication techniques had been so primitive, and they were so vulnerable into attacks and cyber theft and cyber control. But I think over the last 1 decade, a lot of researchers have been proactively figuring out the loopholes and the attack points and attack footprints, and many new standards from the physical layer to the communication protocols and also into the application layer. There are certain standards and good practices to embed secure communication between two different nodes and two different people. For an example, if I talk about certain protocols like lightweight M2M, CoAP, and also OMA DM. These protocols are really designed with security in mind. Those are rock solid. Some of these protocols are really solid. But again, those are dependent on the requirement of the use case. Certain consumer scale applications or the protocols, those are security, but not the highest level of security capabilities. But when you talk about certain other communication protocols like OMA DM, which are used mainly in the network layer, those have many stringent measures being taken to implement security and that particular layer. But overall, in any of these layers, those are designed with security in mind. But when we build applications, obviously when you deploy networks, when you deploy different sensors, and also when we write firmware, this was all done by people, human, and there might be human errors, and there might be overlooks, and there might be certain gaps in the processes, in the process of making them, which are making this entire ecosystem prone to security vulnerabilities inherently. So how to deal with this is, in one way, we need to really have a lot of governance and proper processes in the implementation process to minimize those gaps. That is one part. And the other part is testing, which means not only the application testing, but also vulnerability testing and ethical hacking to find out these different vulnerabilities. So that's the other thing. So all these are really part of that billion-dollar industry which I've been talking about, the cybersecurity. So again, day and day, It's a cats and mouse game. The researchers and the equipment manufacturers and the standard bodies, they are trying to make things more and more secure and robust. But on the other hand, also there are bad guys, right? They also become advanced and they are figuring out more and more different ways to figure out weaknesses and somehow hack into and take advantage out of that. I'll take one example. Are you familiar with Alexa, the home assistant? So recently there was one secret loophole and they were able to hack that. Do you know what they used? Nothing with the network, nothing. I mean, they didn't even go inside the network. What they simply used was, they simply encoded a laser with voice and just aimed the laser from another house through the window into that device, and closer to the mic, they were simply aim the laser to the mic with voice encoded. So with the very simple temperature difference which is made by the laser with the encoded voice, they were able to activate the voice assistant. Okay. So you can hack things in very, very different ways which are not even thought about, and always people will figure it out. But I think in the meantime there are the good guys who are trying to figure out those issues and trying to come up with various ways of eliminating those vulnerabilities, and it's an ongoing process.
Another question. I think in terms of 5G software layer, so they have come up with a microservice container architecture and the linear feed file, so that the modules are getting implemented on the module basis. So that is the security movement.
Correct.
So I think that's one of the reasons that they're deploying the 5G components in the container-based architecture.
Absolutely, yes, yes. So I think even GSMA is highly involved in that process, and then I'm not quite sure that architecture is completely finalized. Yes, yes. So probably maybe they might not be releasing all the components which might have high vulnerability footprints right now. So that is why one reason the 5G entire architecture is not commercially available completely right now. But obviously very soon those will be released. Anything else? Okay, hope I did not make you extremely bored and made you sleep. But this is a tough time after work. I think all of you are really hoping to go home, and thanks for participating and giving me an opportunity of really sharing some of the experiences. And also on behalf of ISL, I'd like to thank once again for making this repeat session once again. Right, thanks.
Thank you. So, good evening to everyone once again. So, it's my great pleasure for delivering the vote of thanks. On behalf of IT and Computer Union Section Committee, I wish to express my sincere gratitude to ISL Secretary and the Organization Committee. Also, I would like to thank Engineer Educator, who has shared his immense knowledge on the M2M communication, especially the Infinity Library, that we hope that the technology to our country is able to offer people so that we can do something to our country. So thanks once again to coming down to Sri Lanka from Australia and delivering your professional speech and the knowledge sharing for this community. And once again, thank to IT Computer Section Committee to organize this session together with ISL. And there's a small drop of appreciation.